last presentation of this tempering and pre-processing session. It's controlling glass and quality during the heat treatment. The presentation will be given by Eric Hegstrom. For more than 20 years, Eric has led the development of glass inspection equipment for Light Sentry. It's now called Light Sentry Soft Solution. He has more than 30 years experience in software engineering, and the last 22 of which were spent designing and developing industrial vision, control and automation systems for glass fabrication. He is active in developing industry standards and was most recently on the ASTM subcommittee for C1901, standard test method for measuring optical retardation in flat architectural glass. His previous work experience includes Apple, Applied Materials and Perking Elmer.
Hello everyone, welcome for joining us. I'm Eric Hegstrom. As Francis mentioned, I've been working for Light Sentry for over 20 years. We build equipment to qualify, to quantify distortion, anisotropy, and defects in tempered glass primarily. And today we're primarily going to talk about, find the right button here. There we go. We're going to talk about state-of-the-art tools and technique for measuring and analyzing the quality of heat-treated glass, either tempered or heat-treated. We're going to touch on many areas, but primarily going to focus on distortion, anisotropy. I think Riku and Peter have done a very good job with white haze discussing that earlier today, so I will leave that out of my presentation. I've attempted to make this kind of a technical presentation, but we sell equipment, so please go to glassquality.com and you can find equipment to do all of these beautiful things. Why do we need improved quality control? I think a lot of this stuff is very obvious. Higher specifications from customers. Furnaces are more controllable now. We're running into a problem with less experienced workers on the line, so we need more automation. And higher throughput's always called upon. We need higher throughput with good quality. So we need quality control systems to maintain peak efficiency. Okay, the zebra board. In the beginning there was a zebra board. We've all seen this. I think distortion, you can see almost any kind of distortion on the zebra board if you've got an hour and a qualified eyeball. The problem is these things need to be measured very quickly. There are two fundamental measurements of optical distortion, and this is very key to the whole understanding of optical distortion. There's optical power in millidiopters, which is typically measured at thousands of points on a piece of glass. It's 100% inspection, and it measures exactly what the eye sees. That's when you see images get bigger or smaller in a reflected image, you're seeing the millidiopter. And then there's also roller wave and edge lift, a peak to valley measurement, which is a two-dimensional wave that's typically measured in the direction of travel coming out of the furnace. It's highly dependent on the type and size of gauge used, and we will talk about that in a minute. And it does not measure what the eye sees. You do not see displacement of the glass. You see things getting bigger and smaller. You see millidiopters. And just a quick overview of what a map of millidiopters on a typical piece of glass would look like. Here's 3 parts you may see out of a furnace, a good one, medium one, and one with some good edge kink. Where it's 0 or green, that's 0 millidiopters, the glass is flat. As it goes up into the red, it's concave. You'll see the images get smaller in reflection. As it goes down to the purple, it's convex. As it goes down to the purple, it's concave, like a magnifying, like on your, and you will see objects get larger in reflection. And then the question is, what exactly is a millidiopter? I know we throw around the term millidiopter, but what is it? It's a very simple term they've come up with. They don't want to use focal length because focal length would get infinite when glass is perfectly flat. So the millidiopter is the 1 over the focal length. I'm sorry, a diopter is 1 over the focal length in meters, and millidiopter is, of course, 1/1000th of a diopter. And I've made a kind of an example chart here on the side to show you what the radius of curvature would be for various example millidiopters, so you can just have an understanding of what a millidiopter is. So let's say at 20 millidiopters, a radius of curvature would be 100 meters. So imagine you have a string running all the way to the end of a football pitch, or even an American football pitch, which is 100 yards, and you move the string back and forth like you're 30 millimeters. that curvature that you're describing there, that would be a 20 millidiopter curvature. So you see how small the measurements we are talking about here. Typically, the human eye in the tests we've done, a trained person like most of you who don't look through glass anymore, who just look at glass, unfortunately, we've all succumbed to that, can maybe see 50 millidiopters, but it is not objectionable. And now when we talked about peak to valley gets a little tricky because peak to valley really depends on what type of gauge you are using. All the specifications are designed, or I should say written around manual measurements and define a specific type of gauge. Here in the European standards, I think many of you are familiar with the EN 12150 standard, which uses a flat solid bar and feeler gauges to measure the roller wave peak to valley and the edge kink peak to valley. And in America, we use ASTM 1651, and they have two opposing gauges, which are flat bottom gauges with a plunge gauge on it. And I think EN 12150 also talks about that too. But it's just important to understand that what peak to valley number you're going to get from the same piece of glass depends on what type of gauge you are using. And that's something that I think a lot of people don't get until they start playing around with it. And that is a kind of a complex slide here, but man, that is a beautiful monitor. So how does an automated system measure peak to valley? I mean, we understand, looking at the spec, how a human measures it by sliding the gauge or using the bar and the feeler gauge. But a system like our system will measure the optical distortion in millidiopters over the whole part. That is our primary measurement. From this measurement, we will create a side profile of the part, a high resolution, two-dimensional side profile. And you go, oh, there you go, that's your peak to valley. Unfortunately, that's not your peak to valley, that's what the part looks like. The peak to valley is something slightly different. It's what the gauge will measure. So we apply your specific gauge, this is an EN 12150 gauge, to your actual topography of the glass, and the red line is what the gauge will measure. And you'll see right here, the small blue line is a simulation of the EN 12150 gauge on top of the glass. And this displacement right here is the actual measurement that the gauge will make. So the red line will show you the actual measurement the gauge is making. So the red line is the number that your customers want or that you'll report as the actual EN 12150 measurement. And on this part, we're looking at an edge kink on the lead and trail of, and you'll pick the largest number in the lead, trail, and middle to get your final results. This part has 15 and 0.15 and 0.13 millimeters lead and trail edge kink and 0.09 millimeters roll wave in the middle. So I would call it a pretty good part. I often get the question is, how do you convert between millidiopter and peak to valley? And I've seen pictures with different wavelengths and such, but even at the same wavelength and the same peak to valley, real glass, there is no simple equation to do it. You have to use a system like we're talking about before with an actual model of the glass. Because this is what a theoretical perfect sine wave roller wave would predict. These two circles are the actual shape of the millidiopters, and the size of those circles are the radius of curvature and describe how much optical distortion they are. And in reality, we'll see things go even often 2 to 3 times as bad as this, and sometimes even 10 like this. We'll see parts distort like this, where they'll have the same wavelength, same peak to valley, but one area will have a much smaller radius of curvature and a much higher part of distortion there. So you just have to keep these things in mind. And we'll just go through, there are some weaknesses to the peak to valley gauge. I'm not going to spend a lot of time on this. It's just a single stripe. It does not measure with the eye sees, and and some of the American gauges don't quantify edge lift. So we get peak to valley severely limited. Millidiopters is often the better measurement to rely on. And then to throw something else into the mix, there's transmissive distortion. I just put this in here, but typically if this is looking through the part instead of looking at reflection, but typically if you control flatness and tempering and are using a thin inner layer, this isn't a problem. It's important to have a system that's been verified with a NIST or other industry traceable standard. All our systems are built with NIST traceable standards. Here we are with a couple very expensive diamond turn mirrors we use for the development of our system certification. Our little sales pitch my boss makes me do. We have 500 systems. We're now partners. Actually, we're the same company with soft solutions, so we have US and EU-based support. Okay, anisotropy. We talk about anisotropy or anisotropy, or there's like 3 different ways to say it, so I get very confused. What we're really talking about is classic iridescence or quench marks. I won't go through the optical definitions. You can look those up. What causes it? An imbalance. Many of you have probably seen these parabolic drawings of compression and stress layers in tempered glass. And if they're perfect, like this, which of course never occurs, any light that goes in is rotated on the way back, so there's no anisotropy. Polarized light does not cause any issues. In real life, there's an imbalance in the parabola, and that'll cause certain areas to reflect light that shouldn't be reflected typically, and other areas to reflect light from the back of the glass that typically would not be reflected. So you'll see those ghostly white patterns that we see here on the glass. And the thing to remember is iridescent requires polarized light. Either you're wearing sunglasses or you're getting blue sky polarization, which is light bouncing off the air molecules on the other side of the building and coming back and lighting up the window, and you're seeing iridescence. Or if you're unfortunate or fortunate enough to be near water, of course water will, anyone who goes fishing and wears polarized glasses will know water will cause a very high polarization effect of the light. But you will not see iridescent effects inside if you're not wearing sunglasses. And this slide just makes it clear that anisotropy in nanometers equals the worst case iridescence you can see in a part. This is 2 actual real life parts. This is the measured average stress in nanometers on the left, and this is a picture of the actual part. So it's just kind of a smell test to show this actually works. And this is what ASTM decided how anisotropy would be quantified in nanometers. And to talk about actual specs, the first spec that was I helped work on was in 2021, the ASTM C1901, which is basically a test method for anisotropy. It did a couple things. It defined optical retardance in nanometers as the fundamental measurement of anisotropy, but it does not set any quality limits. There are no actual numbers in there, but it does cover a method for verifying and calibrating results. So any decent anisotropy system out there should comply with C1901, and you should be able to independently verify the operation. The recent DIN 18198 standard does go a little further and define some quality classes, but they are only for they're only for uncoated glass, which is not, I would say, probably not as useful as one would hope, because anisotropy is often showing up in coated products. And these are some of the ranges, and I think the 18198 is very easily available. DIN 18198 also defines some levels of sensitivity to anisotropy. We have found in operation most people making monolithic glass going to the half wavelength of green light, with its 265 nanometers, is a sufficient range. But advanced systems, we offer a system, and I think other people do, can go all the way out to 1,000 nanometers, which are important for laminated parts or some very thick parts. And optionally, the spec says it's optional, but they can provide what's called an azimuth angle, because parts will add or subtract based on the angle of the anisotropy. So if you're laminating 2 parts together, if their angles are the same, the anisotropy will add. And if they're opposite angles, they'll actually subtract. So if you're going to try to model the visual characteristics of these parts using anisotropy, knowing the actual azimuth angle is very helpful. This is a quick slide to show that anisotropy and distortion are distinct. I won't spend much time here. On the right is a part with high distortion, low anisotropy. On the left is a part with low distortion, but this high hoop stress anisotropy, which can now often cause a bistable kind of saddle bow condition. Analysis and feedback. Measurements are great. It's great to have the raw numbers, but what do you do with them? You're running a plant, you need to get quick feedback, you need to be able to make decisions quickly and adjust your process. The most basic quantitative metric to use is a cumulative percentile. And that's basically saying this is a part here, and this is the cumulative percentile of the distortion. And basically we're saying 80% of the area of the part is under 88 millidiopters, and 95% is under 303 millidiopters. So you can set up a variety of quality thresholds based on those numbers at any level. And the same type of thing can be done for anisotropy, but with, instead of millidiopters, cross out millidiopters, write in nanometers, and you can define tests in the same way. And that's a great place to start. That gets you somewhere to know the general level. But here's just a slide of a couple common anisotropy, a couple distortions, roller wave, pocket distortion. The interesting thing about pocket distortion, we'll go to the next slide, there's many different types of distortion. I won't go through them all because we're kind of pressed for time here, but you can see the glass can distort in many different ways other than just standard roll wave or edge lift. And this is where advanced analysis comes in. Because many parts, such like a pocket distorted part, if you were to run a gauge on this part, you'd go, oh, this part's perfect. It's got like 0.03 millimeters distortion. You go, this is great, so let's sell it. But when you put it in the window, you'll see the same problem we saw back here. You'll see this kind of stuff, and so your customer's not gonna like that. So it's important to have a system that'll flag pocket distortion, they'll pull out this pocket distortion and flag it in real time. There's also something called cross conveyor distortion. It's this fine fold line that you'll see running in the direction of the conveyor. And this, you're hard pressed to even see this on the zebra board when you're looking for it. So it's important to have a system that will pull this out and call it out and mark it with the red X and tell you to reject it or adjust your system. There's another advanced analysis looking at anisotropy. I know we talked about belly banding. This will find like high anisotropy levels in the center of the part and tell you have possible belly banding issues coming on. It doesn't actually identify the white haze. It just tells you that your part has a condition of internal stress that may cause it to rise up on the rollers. Adaptive quality control. When you're running many different parts, you're going to want to change your quality control levels based on what your customer wants, what the project specifications are, what the part geometry is, because certain parts are more likely to distort in certain ways. The inspection locations on the part, if you want to limit it to the view area, and the part thickness and coating. And this is very important because this is something that's really coming very to the forefront now. Thinner glass and certain coatings are harder to control, so there's a capability issue, and objectionability. Let's talk about this. Put simply, reflective coatings have more visible distortion and anisotropy. It's been widely known in the industry, and it makes intuitive sense that reflective distortion will be more visible on a highly reflective part. So when you're tempering a highly reflective part, you're going to want to control distortion to a lower level. And Francis and Saint-Gobain have done some very good work doing the same, quantifying this for anisotropy, something called sigma QM, to quantify the visibility of quench marks based on the coating reflectivity and transmission. I know I suggest you read their papers. It's a lot of great stuff, and it goes into great detail that I don't have time for here. But what it comes down to is you're going to want to actively adjust quality threshold based on the coating and the thickness of the part. And the only way you're going to do that is either enter it manually, count on the operator to actually enter those values, supply it from an ERP system, hope that no parts are lost in the way, or have an online sensor, such as a sensor we make, that will identify the coating and the thickness and make an automatic adjustment to the quality. Load-end systems, I just want to go over, there's a few load-end systems available that will provide automatic recipe selection going into the furnace. We'll make a recipe selection based on size, location, and coating type, and then make an adjustment to the heating and quench times based on the bed load area. And the interesting thing is if you can save 10 seconds on each load waiting for an operator to enter a new recipe, you can potentially save 5,000 loads a year if you're running 24/7. And that's something a lot of people don't think about. These systems also provide a load validation, checking for parts that are too wide, too long, broken parts, corner off, long loads, all sorts of things that can cause problems in your tempering oven or your coater, and it'll stop the load before it goes in, saving one afternoon shutting down a tempering oven to fix a problem like this almost pays for a system in itself. There's some great online tools for verifying tempering level. The GASP surface polarimeter, I'm sure many of you have used these. It's the only certified system to actually measure surface stress online. And automated cullet testers, which allow you to break test the glass, keep the cullet, do a full count of the cullet, find the small and large pieces, apply whatever standard you're using, keep it all in a database in case there's an insurance claim or a lawsuit or whatever comes later. You can prove that you have done your tests and this was the results of them. And then we get to intelligence, tying it all together. We got a lot of information here. What can we do with it? We can throw it in a database, bring it up on an archive server. We can have some nice, simple PDF reports of every load that goes by with a summary of the results. And a very powerful tool is called the interactive viewer that you can give to your customers with the data so they can actively view the data. I've talked to a couple customers of ours who they'll put up a building. Their client will say, 4th floor, the glass looks bad. Everybody will go out and argue about it. That was the old days. Now they just send them the files. They look at them. 90% of the time they go, they're in spec. There's the data. What can I argue? End of case. So that's a great thing. Also, there's 2 more things I just want to touch on before I end here is automated reports and alarms. We now provide a new smart report. You can set it to come up every shift, every morning, once a month for the monthly reports. These will be emailed to all the people that it's important. It's a smart report allowing you to see what ran over the night, what ran over the month, what ran over the last week. You can click on, say, I want to see all 8mm parts with coding E3, and it'll give you a nice summary of all the parts run and your production. So you don't have to go out and pull reports. These come right to you. And the latest cloud-based production monitoring allows real-time monitoring and push-based notifications. And I don't have a lot of info on that, but that's a new product that Soft Solution, our partner, is driving. And missing part notifier, I think it's about the last thing I'm going to cover. If you have an inspection system on the load end and on the unload end, an Osprey, a distortion system and a load system, now you can do some magic. Now the system can say, well, 4 parts went into the oven, 5 parts came out, something must have broken. Or 4 parts went in, 3 parts came out, we lost a part. It'll notify the operator, they can go and do whatever they need to do, reorder the part, and it keeps it all in a database there. And of course, we offer all the surface and edge quality stuff, but we do find this is often better to do right after cutting or before the IG layup. And logo verification, sightline inspection, grid alignment, all that fun stuff. And just to step back about online thickness and coating measurement, this is an example of one of our sensors that will discern pretty much, I don't want to say every coating type, but it's everyone who's tried it out has been impressed that we can discern every coating type in their factory once it's been trained. And these systems will identify coating and thickness and drive our systems to automatically adjust their quality control thresholds. Thank you.